somehow maybe I feel I should shortly, because we just have it on the screen, I should maybe shortly repeat what we see here. Yeah? So when you have this inverse pole figures, once again, what you display there is in which crystallographic directions point certain sample directions. So we are looking for features in the sample which are related, of course that's what we always search, which are related to certain crystallographic directions. And this is very often more easily visible in an inverse pole figure than in a normal pole figure. Why that? Because you can say from your knowledge about your sample what is a preferred sample direction. For example, in a rolled material we know the preferred sample direction is the rolling direction. Or in a sheared material it's the shear plane. Or and that may be in geology important, no? That you say I'm interested in the shear direction. And in a sputtered sample, it may be the sputter direction or something perpendicular to it. But you don't know which crystal direction is relevant for this normal direction, yeah, or for this rolling direction. You don't know it by heart. No? You know, okay, my material has been rolled, it has been extruded, it has been, I don't know, we have done severe plastic deformation by angular, now what is it called? ECAP, exactly, equal angular compression. So you have done ECAP on the material and you want to understand how does the sample react to that. So what is known to you is the sample direction. So I know I'm interested in this 001 sample direction. That they write it here with square brackets, which usually indicates that we are talking about a crystallographic direction. So I would, whoops, hello? Come back. I would even think that this is not the best selection, what they write there. Yeah? There should be, I don't know what kind of bracket we should select, but what we are not doing, this 001 is not a crystallographic direction. It's a sample coordinate direction. Yeah? And that means, I start plotting for you again, our most simple rolled material. Yes. So we have our x direction, x, our y direction, y, and z. So, and now, and this one here, they call here 100. This is confusing for many of you. If you have learned, okay, square brackets mean crystallographic direction. It does not mean it in this case. No? So I don't know which kind of bracket one should use there. This is already all used. No? You have this is used. The curly one is also used. Oops, this is fantastic curl. And the round ones is also used. So I don't know, there's maybe no other easy, maybe one could make just a straight line around it or something like that. But anyway, it's a little bit confusing that this is indicated in the same way as is crystallographic, but it does not mean it. But now you could say, anyhow, I don't need to look exactly into one of these directions. I could also look into a direction which is somehow this one, which would be, for example, 2 in x, 0 in y, and 1 in z, something like that. Would be somehow some inclined sample direction. Why would one like to do that? Why is not always important to see into these sharp directions of my sample? Yeah? First, in a geology, that may be, of course, anyway irrelevant because your sample has been sheared somewhere relative to the cutting out of your sample. But even in a rolled material, you remember perhaps from yesterday, I showed you that the surface has a different texture than the center. Surface like that, and center like that. And now the surface has, of course, experienced the action of the rolling cylinder. Yeah? So here was the rolling, and that means there is some shear going on. when you're on the bottom, and some shear when you are on the, let me see, when you are on the top. And this shear action is no longer going in the direction Z, but it's going at an inclination angle towards this. And in order to see that properly, you may say, it's better to select a plot direction where I'm looking under a certain angle rather than exactly under Z, X, and Y. No? That may be, and actually I hope I find that now. I have a nice example for that. I will not do it with you because it takes a little while to really figure out the right orientation. But isn't it in here even? Oh yes, it is exactly in here. Yeah. So Lamia disappear. Good. It was exactly this example. I have it right, correct in mind. So this is EBSD for texture evaluation, just what we are doing, what we did, and I showed you this this example here already. Exactly that's what I meant when I showed you this. So we have a texture component down here, a texture here, and a texture here. And we had this typical texture components here. So, and now I was going to analyze the surface textures in a little bit more detail. And actually, it looks, this pole figures here look symmetric. So there is a clear symmetry, but they look only symmetric because I took the lower one and the upper one and add them together. And if we look into the lower one only or in the upper one only, we will find out that it's actually not symmetric. That the lower one has an inclination like that and the upper one has an inclination like that. And that is because they were rolled in a well-defined direction, and the shear force which is rolling, which is actually creating the deformation, is not symmetric. It's an asymmetric force. Here in the center, it's perfectly plane strain. That means the grains are just pancaked and elongated. No? It's a pancake rolling, and then you get a really symmetric texture. But on the surface, it is not, and that is shown here. So this is the center. And actually, here I selected the following writing. Instead of using these square brackets, I said I don't use any brackets. Yeah, so I write the crystallographic directions with the conventions. So sharp brackets means all 110 directions, and square brackets means only one particular 110 direction. And the sample direction I indicate without brackets. So if I plot here for the center of this area, I plot in which how many crystal directions of 110 type point into the direction 100 of the crystal, and the 100 direction, let me guess what that is. 100 is probably this direction here. Yeah, I didn't plot it here. Again, a mistake when you print such things in your thesis or in a paper. You should always make a little coordinate system next to it, showing where is X and Y. Huh? What do you mean with X and Y? But now, if I now look on the surfaces, I found there is a different texture component. But this texture component is actually not, when I plot my stereographic projection, I find this is not symmetric. It's not exactly in X direction, not exactly in Y direction or in N direction, but it's actually inclined by a little piece here. And didn't I select exactly? Oh, 201, yeah. So I still obviously have this in mind. That's why I selected this. If I plot the 111 directions pointing in to the direction 102, then so that means that's some sort of inclined sample direction. Then I find a maximum of the distribution, but I find that the maximum of the distribution is stronger on the top side than on the bottom side. And then I take the other one, which is the 111 direction parallel to the -02. So that's the one is inclined like that and one is inclined like that. And I find this is stronger on the bottom side. And this indicates that the sample has been preferentially not rolled in the same amount back and forth, but it has been preferentially rolled only in one direction, and therefore the shear was always constantly like that and like that. And that leads to this inclined textures. No? Usually, if this would be a homogeneous rolling, this texture point would be centered in the middle, But you see clearly when you're observing the text, when you're observing the pole figures, you see that this is inclined. And now you can go and plot these textures here over the thickness of the sample. And here I plotted just how many red grains do I have by integration at slices here along y. This is the y position here, and I show here how the 110 parallel to 100 texture component behaves, relatively symmetric. And if I do it for the other two texture components, you find it's really asymmetric. Yeah? And from that, so you have a peak on the here on the lower side and here on the upper side. And I can now not tell you what this indicates, or yeah, a little bit yes, but I cannot quantify exactly how important it is. But it shows us that there was an asymmetric rolling process going on. Yeah? I mean, rolling is never symmetric. No? It's always from thicker to thinner. No? It's not on both sides of the rolling mill, it's equally thick. So there is shear forces which are asymmetric. And these shear forces we see. And you remember my example with the Gauss texture. This Gauss texture which leads to this enormous Gauss grain growth. And these Gauss grains in these rolled materials, they grow only very close to the surface. They don't grow out of the center of a material, they grow from the surface of the material. And, oh yeah, this is actually iron silicon. This is the same material. And we know that the action of a shear force leads to different rotations than the action of a pancake rolling. Yeah? Of course, you see it here. It's clear. Must be, because the surface has completely different texture than the center. Yeah? And this action of a shear force leads then to the formation of nuclei for the Gauss. And by doing a very careful analysis of this texture components, I haven't done that, but let's just make an example. You could tell, there is a particular sort of shear going on in the surface and in the two surfaces, and by changing the diameter of the rolls or by changing the temperature of the rolling process, you could modify that. You could make it stronger or you could make it weaker. No? When, for example, when you are at higher temperature, usually the shearing becomes stronger because there is more sticking of the rolls on the material. Yeah? Then the shear becomes stronger. And by better lubrication becomes lower. So you take more water into the rolling mill, you will reduce these things. And this could have, here I don't know, but it could have very important consequences later on for the final rolling sheet and for the final product properties. So that's why it is actually not only an academic exercise to show that you could look also in any kind of direction, no, for this material. So you could select any kind of inverse pole figure, and then your inverse pole figure would be, so once again you would have your triangle, and you would not write 11001, but you would write 102 on it, no? And you would get then your intensity distribution. In this case here, 102, if you plot the 102, you would find, there's obviously a concentration at this corner here, no? If you plot the 102 sample direction. And that is then this here, no? Okay, good. That as a repetition and as a additional information on it. Is there something more? Oh yeah, now we come to misorientations, and we do that only after I have taught you properly misorientations. Now this falls apart here. Why that? Did I lose something on it? No. Good. And I need my misorientation story. Where is it? We keep this on, yeah? Mm-hmm. Here. Yep, just a few slices about it. Actually, I will not show the whole story here about misorientations, but just from here on. So, crystal orientations, what's that? So this we had, of course, yeah. You remember yesterday in the beginning I showed you what is a crystal orientation. It's just the rotation of the sample into the crystal. And now we go to misorientations. And misorientations is not a big extension of that. We are only now not measuring the orientation of a crystal with respect to the sample, but we are measuring the orientation of a crystal with respect to another crystal. So instead of having a sample here, I have a crystal here. Yeah, and that's in principle all. Okay, so let's do it like that. This is not what I wanted to show. Is it not going on? Oh, now we are coming. So it's a rotation. A misorientation is a rotation that transfers the coordinate system of one crystal into that of another one. So this time we have not a sample, but we have a crystal, and we have a second crystal there, and we rotate again between these two. So in principle, not different from what we have seen already. And now, however, the thing changes a little bit. So we have before we had S and C, and now we have C and C. Yeah? So that's important. And the misorientation, the orientation was called O. The misorientation we call delta O, or unfortunately I don't keep the notations proper, delta G, because often the orientations are called G. So delta G means the misorientation between this and this crystal here. And I hope I'm showing you the latest slide on it. Let me see shortly. Yeah, but it looks okay. At least enough to explain. Good. So we have one crystal with respect to the other. And now we need to do a little bit of exercise to follow up completely. So there's one crystal, which is rotated with delta G into the other crystal. Or inversely, you can say the misorientation between these two crystals is the first crystal multiplied with the inverse of the second one. So you just resolve this equation for delta G, because that's the one which we want to measure. Okay, and now comes an addition to it. Each of these crystals has crystal symmetry, yeah, which we indicate by L. So you remember the cubic crystals, for example, have 24 different ways of rotating them, and each time it looks physically identical. So if I multiply my crystal C2 with its crystal symmetry, then it will be C2 times, or L times C2 will make one version of this crystal. And the same I can do with L times C1 will be also one of these symmetrically equivalent versions. Once again, the crystal would not look different, just the numbers would be changing. And of course, once I have done this calculations here, I can still multiply the symmetry elements onto it. And now we, as I said, for the crystal C1, we have J possible crystal systems, symmetry systems, and for the crystal C1 we have I1. So in principle, we can describe this misorientation by a combination of altogether I times J different misorientations. And if this, for example, if the crystals are both cubic, then this I and J run both until 24. So we have 24 times 24 different descriptions of misorientation. N times N possible misorientation expressions. And this is, where is it written, how many we have in the cubic system, but 500 something like that. 576 or so, yeah, 24 times 24. And so the question is now, we have these many descriptions of orientations, which one is the right one? And I should show you how different they look like. So, come to my computer program here. Yes, I have two crystals, 1 and 2. Fantastic, yes. Goniometer is 0, even, yeah, great, okay. So I have two, let's put them up here. One crystal and a second crystal. They have really some really different orientations. And now I calculate the misorientation between these two crystals. So I say this one, delta G with this one. And now it calculates this misorientation. And we can say show all. And now we get a long list of misorientations. Actually, 576 different misorientations. And they are looking quite different. If you look on the numbers here, so for example, and I forgot to once again going back to my presentation. Now we need a different way of presenting them. How can I do it here? It's quicker. Here. We describe it in this form here. So I expressed that already when we spoke about the Rodriguez space. You describe it as an angle of rotation and an axis of rotation around that, around which you do this rotation. Yeah, axis, angle, one axis and an angle, and that is the usual way of describing misorientations. Good. So we are doing that. Also, I need to go back to my TOCA program, and that's no, there it is not. Where is it? This one. And that's what is displayed here in this list. Here is the angle, and here is the axis of rotation. And for example, you see these two crystals are misoriented by 97 degrees around an 0.36, 0.39, 0.85 axis. But they are also misoriented by a 177.92 degree around 0.40, 0.9 degree. And by 100 degree rotation, each of these rotations leads to exactly the same rotation from one crystal to the other. Yeah. So which one is the right one? Which do we take? Yeah. When I want to report that in a paper, or when I want to write this is a large angle grain boundary, is it 100 degree? Is it 177 degree? Is it 46 degree? 133 degree? What is it, this boundary? No? And actually, one has created a definition, and that's purely only a definition. There is no physical reason to select that. It's just in order to make it easy, make life easy for us. One has decided to take that one, which has the smallest rotation angle of all this list, and whose axis is in the standard orientation triangle. You remember the standard orientation triangle of cubic was this funny little triangle where all possible axes appear once, and this is the definition for misorientation. Can also, if you have two faces, yeah, you can also do that. No? It's also valid when you have austenite and ferrite and calculate misorientation. The same definition applies, and in this case here we come to the misorientation 43 degree around the 001 axis. Oh yeah, this shows that it's obviously some sort of special orientation. Yeah, 43 001. I don't know. I selected something special. We see here that there is obviously some overlapping planes here as well. Obviously, I rotated by chance, I believe, such that there is a special misorientation formed. Anyway, so this is the definition. And every software which knows that, which is used for that, knows that, and needs to do all these calculations first before it then can propose to you the misorientation is that. So this shows you already that this definition of a large angle grain boundary, something which is larger than 15 degree or so, is a little bit random, yeah? Whether you say it's 15 degree or 170 degree or something like that, it's a little bit random what kind of number you tell there. No? Good, but this will come later. So this is the misorientation. Yeah, and it was here already. Come on. Okay, and we express that, so we express it in this notation as axis angle or Rodriguez vector, and as misorientation, as disorientation, we report then this value, which is has the smallest rotation angle and axis inside of the standard orientation triangle. So now, important to remember, misorientations are rotations and not only angles. Yeah, often you say the misorientation is 10 degree, But this is not a complete misorientation. No? The misorientation needs an axis and an angle. However, it's true, and you say, I want to distinguish whether I have a large angle grain boundary or a small angle grain boundary, then you may say, the misorientation is 15 degree, without mentioning the axis. Everything below is small angle grain boundary, everything above is large angle grain boundary. Are you familiar with why that is like that? Do you know that? Why we select 15 degree as the border between low and high angle misorientation? Someone is aware of it? Huh?
Boundary energy.
Boundary energy, yeah. Yes, okay, exactly. So that has been taught probably, yeah. In a low angle grain boundary is constructed out of dislocations, yeah. So I see that it's not known to everyone. That's why I make just a quick picture. I think it comes also in this presentation. I just didn't plan to show it, but it's very quick. So if you have a low angle grain boundary, so here is the lattice plane from the first, and here's the lattice plane from the second crystal. This misorientation is made by the existence of dislocations, which actually have a regular distance to each other, relatively regular distance, and a unique type. And the more dislocations you have, so the denser is this dislocation the denser is this dislocation network, the larger is the misorientation. Yeah. So when you have 1 degree misorientation, you have about every 50 nanometer you have a dislocation. Yeah. And when you have 15 degree, then you have every 2 nanometer or even less you have a dislocation. And when you're at 15 degree, the dislocations get so close that the cores of the dislocations overlap. And at this moment, the dislocations move together. There is no dislocation any longer. And the grain boundary behaves completely different than before. It's no longer separated by individual dislocation features, but it's then separated by a kind of an amorphous feature. Yeah? Sometimes you still find some features in there, some regularities, but you can consider that the direct grain boundary is kind of amorphous, yeah? A random arrangement of dislocation, particularly when you then start deforming it, it often has no regularities any longer. And this is, of course, visible in the energy of the boundary, but it's even more characteristic is actually the structure of the boundary. And there you can actually, then the misorientation just as a rotation is about sufficient, not fully, because you still have to distinguish between between tilt and twist boundaries. And we'll come to that in a second with it. So, oh yeah, this is actually here. For general grain boundaries, the angle alone is maybe often sufficient. But for special boundaries, for example, twins, the misorientation needs to be quantified as a total. You cannot live with only the rotation angle. You need to have the axis as well. And if you want to say this is a twin, then it's not sufficient to say it's 60 degree, because there could be many other 60 degree boundaries which are not twins, and just only the 60 degree 111 twin, boundary is a twin. No? And it's still not sufficient. If you, in twins, you can decide, is it a coherent twin boundary or is it an incoherent twin boundary? Coherent means that the plane where the two grains meet is a 111 grain, is a 111 surface. Yeah, that is a coherent twin, and the rotation must be 60 degree, the axis must be 111, and the plane must be also 111. That means we have altogether 5 parameters to describe this misorientation or this grain boundary in this case. Yeah, so you need even more, and if it's not 111, if it's your 60 degree rotation and 111 axis, and not 111 twin boundary, 111 boundary, then it's an incoherent twin. I'll come to that in a moment. So we have then the rotation, which is 3 parameters, and the grain boundary plane, which is 2 parameters, altogether 5. And then, with EBSD, of course, usually we get only 4 at maximum. Why 4? Why not 3 only? The misorientation is clear. Misorientation is 3 parameters. It's the rotation, yeah. of course, we express it as angle and axis, but in principle, it's only 3 parameters. And what's the fourth parameter? The fourth parameter is the trace of the boundary on the surface. This is not directly misorientation, but misorientation often related to boundaries. So it's this line here on the surface of a material. But okay, I don't want to talk about that in big detail. Do I want to talk about that? Yes, I want. This is an EBSD map of, what is that material? Some austenitic stainless steel, I think, or nickel superalloy, I don't know. So at least FCC. I don't remember what it is. And I have plotted all grain boundaries in here. In black, just general large angle grain boundaries. In yellow, very few of them, just general small angle grain boundaries without taking care for what kind of axis they have. And in red, sigma 3, and in green, sigma 9 boundaries. Now, it may be that you're all familiar with the sigma concept, with the CSL concept, but I will shortly explain it. So if we just look in the normal distribution of angles, of misorientation angles, and we show how many of them we have in this map here, we find actually there's not much happening, not many of these grain boundaries happen if you plot it over angle, but then we have a peak here at 39 degree, and we have another peak here at exactly 60 degree. And actually I write for you now already that this is sigma 3, and it will be turning out that this is mainly coherent twins, but it's not only coherent twins, it's also incoherent twins in it, and this is sigma 9, which is a twin in a twin. And we'll come to that in a moment. But now, so this was only a 1D distribution, and I tell you that this is sigma 3 and sigma 9, but by just looking on this graph, you can't tell what it is. No? You can just say there is a 60 degree boundary and a 39 degree boundary, and then there is some other boundaries just randomly distributed in between. Now, we can become a little bit more detailed by saying, now the EBSD software, or the EBSD analysis software, allows us to go and see not only the angle, but also see the axis, of rotation. And how can we plot an axis? We can again use our standard orientation triangle and plot the direction of rotation in this triangle. So if it's an 001, then we plot it here. If it's 110, then it's there, and 111 there. And we can now plot the following. You say, I have an angle and I have an axis. If the angle is between 0 and 5 degree, I make one axis plot. Between 5 and 10, I make one axis plot, and so on. So all together until up to the maximum possible misorientation angle in a cubic system, which is 62.3 degree. You maybe remember it from the Rodriguez story. We are plotting these angles, and for each of these angles, we are plotting which axes appear in this map here. And then we see, long time not much happens, but when we come to 60 degree, we see a strong concentration here in the corner of 111. Yeah, so that obviously indicates that there is something specially happening. And at 48 degree, there should also be something. It's not very strong. It's too few of the green lines here to see it properly. But if you would be here at 48 degree, you would find that there is a concentration at 110. Okay, so obviously there is a lot of misorientations of type 60 degree 111 and of 48 degree, 49 degree, no, what, 38? Oh, yes, 38. I need to look somewhere else. It must be here. But still, it's not very, very strong. But there is a little concentration here at 110. So these things you can see here now. You can see that there is certain preferred misorientations, and I will show you in a moment that this is very strong, has a very big potential to look on misorientation data. But, oh yeah, is this coming already now? Yeah, good, then let's go for that. So this plot of 3D distribution, this will be now used to understand misorientations between alpha and gamma between alpha and gamma phase in a steel. And actually this steel is the following. Unfortunately, I don't have I need to show you this, I'm sorry. Too much scientist to leave it out. Where is it? It's It's not in this. I think it's in here. Yes, there it is. Okay, fantastic. Let's take this one here. It's better. Good. Good. So, I believe you're halfway familiar with the so-called TTT diagram, yeah, where you plot here the time and here the temperature, and then you let a sample cool down with time from a well-defined start point, for example, from a perfectly austenitic area all the way cooling down to room temperature, and plotting in which kind of phases are forming while the sample is cooling down. No? For example, when I cool down along this line here, after 100 seconds approximately, it starts forming perlite, and then it cools down just as perlitic. And actually, so we start with an austenite, purely austenite, big grains of austenite, and if we cool it down here along, we get just a purely perlitic structure. If we cool down here along the bainitic, through this perlitic bainitic area, we get a bainite structure. If we cool down very rapidly and we are, go back. If we are cooling down along this line here, we are avoiding all touching these noses here, then we are here transferring the microstructure into martensite, or bainite martensite. And if we make an interesting treatment, which is following like that, okay, then we get a very interesting microstructure. So first we avoid formation of perlite. We are not touching this nose, no perlite in there. And then we stop the cooling. We wait until bainite has formed, and then we cool further down. Yeah? And then this bainite has formed actually exclusively at high temperature. And during this bainitic transformation, which is a displacive transformation, which nevertheless has still diffusion of carbon available, the lattice transforms and pushes the carbon out into the surrounding austenite. So there is still a lot of austenite, and some grains start growing in a bainitic manner. They push the carbon out into the surrounding austenite, and at the end there's so much austenite, so much carbon in the austenite, that the austenite doesn't want to transform any longer. It becomes very sluggish, and then when you cool it down, you can keep a microstructure which has no martensite, only a little bit of blocky bainite, and the rest is austenite. It's metastable austenite, just supersaturated austenite. And when you then start deforming this austenite, it transforms into martensite. We have a strain-induced martensite, and we call this a trip effect, transformation-induced plasticity. And so this is a very nice way of making stronger and more ductile steels. So we cool like that. And I want to show you now the microstructure resulting from this cooling. This is not the correct here, the bainite. No, this there's even written, yeah. All right, so this looks like that. So this, what we see here is an EBSD map, of course, yeah. How could it be different with me? And the gray areas here, this is all austenite, so FCC, and the gray shaded area, this is all ferritic or BCC. Whether it's ferrite, I don't say, but it's definitely BCC. And the different colors here, so the first colors what we have here is actually the grain boundaries. And I have colored the grain boundaries between austenite and ferrite using this software. And you see here a very strange color code, which has misorientations between 40 degree and 46 degree. Why the hell 40 degree, yeah? And we will see that in a moment. And then there is something further information inside of these grains here. I'm also plotting misorientation information. So I have plotted the misorientation across the boundaries here. And inside here, the gray value means the misorientation of this particular point with respect to a reference point somewhere in the center of this grain. I don't remember which reference point I selected. I think I simply said, I click on this point in the center, and it will color the rest of the grain according to the misorientation of this point with respect to this point. And then we see that the grain, the ferrite grain or the BCC grain, is not homogeneous in orientation. Although it has been created at 650 degree, it has orientation gradients inside. Orientation gradients means dislocations inside. where do these dislocations come from? And why do we have these strange misorientations here? So, now in order to understand the misorientations, these special gamma alpha grain boundaries, we need to look in more details. And I plotted here exactly what I showed you before. This is the misorientations, is an axis angle pair, all the way from 0 degree to 63 degree. And what you see here, okay, here this is between 0 and 5 degree, it's homogeneously colored. This is due to the fact that the EBSD system is not so accurate, and you get, for these small misorientations, you don't get an accurate axis. But everything else, what is higher, is quite accurate. And then you start seeing that there's concentrations at certain places. Now, and I know that mainly the misorientations are at 41 to 46 degree. I see it here, actually it's all colored. So let's zoom into this area. Yeah? Let's zoom into this area between 40 and 46 degree. And that's what I'm doing. Come on, zoom, right. And then I see actually more detailed that there's actually a well-defined peak here. Yeah, all the misorientations are actually collecting at this particular position here. All the misorientation axes are collecting there. And now I start scratching my head. That must mean something. It's obviously some 40 degree around an axis which is I don't know what that axis is, but I read it out here because I know there must be some. I knew before there must be some relationship between austenite and ferrite. Probably there has been some sort of crystallographic transformation going on. Yes, it was bainitic transformation, and possible bainitic transformations could run with a Bain transformation or with a Nishiyama-Wassermann or with a Kurdyumov-Sachs orientation relationship. And then I write down what would be the possible rotation axis for this transformation. Bain means actually that the 001 planes in the gamma are parallel to the 001s in the alpha. And the 110 directions in gamma are parallel to the 111 in gamma, in alpha. And from that you can calculate what is the resulting misorientation, and it would be 45 degree around 001. So that would be 45 degree around 001, 45 is here, and there should be here in this corner, that should be the Bain rotation. And if you look, Nishiyama-Wassermann should be 46 degree around an axis 8, 20, 96, 97. And Kurdyumov-Sachs should be 43 degree around 17, 17, 96. So let's plot them in here. The Bain I mentioned already is here in this corner. The Kurdyumov-Sachs, also there is a Bain, the Kurdyumov-Sachs and the Nishiyama-Wassermann. And actually what you figure out now is, that's a clear indication there is obviously one of these orientation relations active. Yeah? There's not a random boundary between gamma and alpha, but there is actually a well-defined crystallographic relationship between them. And if we look exactly, we find, it's actually changing over time. Not over time, over angle. So we obviously have some distribution of misorientations. Yeah? And if I miss this in my graph here, if I would plot the Greninger-Troiano orientation relationship in, it would be right in the middle of this distribution. It would be here, actually. That is the Greninger-Troiano, and this fits best to this misorientation. But we see the misorientation is not constant. It is changing from place to place. And beautifully, you can color your grain boundaries to show which color do we have? No? Which orientation relationship do we have? And orange here, what I see mostly here, I see orange between orange and green. So it's somewhere here in the order of 44 degree. And we could see which one is 44 degree. Now it's pretty much exactly, unfortunately, exactly between Kurdyumov-Sachs and Nishiyama-Wassermann. Very close to Greninger-Troiano. That would be pretty much, this here would be the maximum. Yeah. But there are also areas which have this blue orientation relationship. Now what actually happens is, and then of course I forgot to mention, you have these interesting gradients of orientations here. So from the fact that we have Greninger-Troiano, or actually something close to one of these relationships, we could tell, is this a a hard transformation or is it a soft transformation? Is it a high temperature transformation or rather low temperature transformation? So is the material reacting more in the direction of a Lass martensite or into a plate martensite transformation? We could conclude from that. But in this case it's neither nor. It's a bainitic transformation, and this bainitic transformation actually started here in the middle, and so there was in the beginning this wall was all austenite. Yeah, it was everything homogeneously austenite, and then some little grain started to grow out. As long as the temperature was high, the ferrite just grew, and then the temperature got deeper and deeper, and suddenly it started to transform as a bainitic transformation. And that's the moment when we see this formation of these gradients here. Gradients because suddenly dislocations are forming. And these dislocations collect here and make this orientation gradient. And they grow, and then finally they cannot grow any longer because the austenite is supersaturated with carbon. Then the austenite is left over here, and we can clearly see that we have this typical orientation relationship then. So we can learn quite a lot from just an EBSD map and doing a proper orientation calculation here. Was there a question? No. Oh, good. This one we had seen already, and that's what I wanted to show you on. Yes, please.
You just commented about this martensite lattice or
Yes.
the form. That is depending upon, how did we conclude that actually? You said
From this picture which I just showed you, there is no martensite, of course. It's all bainite. Huh?
yes, but
If
just
in
a
given
hard.
microstructure, if you have martensite or bainite, how to distinguish them?
Ah, yes. What a bad question. No, but this is really I'm coming to this in a moment. No, it's not a bad question, of course. It's a good question. Bad question because I don't have a good answer. So I blame the question for having not a good answer. No, it's really difficult to say the distinction between bainite and martensite. But I will comment on that in a little moment. The reason is, in principle, both structures are formed displacively. And one at a higher temperature and one at a little bit lower temperature. And that means the process in principle is the same. It's a displacive transformation. Just the stresses are different. Yeah, and these stresses lead, depending on whether you have a hard or a soft material, you can relax these stresses or you can't. These stresses lead to the selection of different pairs of bainite or martensite. So when an austenite transforms into martensite, it forms many variants, as you see it here on this picture, which was now on. No? So it forms all kinds of variants. And these variants are not formed for nothing, but they are formed because during this phase transformation you have the shear and you have the volume change. And this volume change leads to the formation of very high residual stresses. And at one moment the residual stresses become so high that the variant cannot grow on. So another variant starts to compensate these stresses. And now and of course, by forming a new variant, you're forming also a new boundary. And now it's a question, which process wins? Is it the energy of the boundary which determines which variant is formed? Or is it the stresses of the or is it the residual stresses which determine which variant is formed? And this one you can see. Which variant pairing you see? Do you see something which is boundary controlled or something which is stress controlled? And the martensite would be stress controlled because the martensite is much more stressed. And a bainite, which is formed at higher temperature, is usually boundary energy controlled. And therefore you can see, you can make the difference, but only by properly considering. The software cannot tell you. You must think yourself. By finding out which variants you have, which variant pairs you have, you can say, is this more probably stress controlled or grain boundary controlled? And for this I can recommend to read a beautiful paper by a Japanese group, Furuhara, and I need to look it up, but I wanted to show you. It's a very beautiful work. Furuhara is one of the authors, that's for certain. What are the other names? He's not the first author. And it's called Say again?
Hectameters of papers came from Japanese.
Yeah, exactly. It's not, it's variant pairing or something like that. It's on the pairing of variants during gamma alpha phase transformation. And this is really a fantastic paper, and I wanted to make with you a little exercise on that. Yeah. But the direct answer, can I tell, is it bainite or ferrite? Is it bainite or martensite? I cannot give you, because it depends on so many variables, and you should also know at which temperature was the transformation. And of course, maybe sometimes you need to look, do I see carbides or do I not see carbides, in order to say that. Here it's, in this case, which I showed you here, where was it? This one here, it's pretty clear. This is bainite, because the bainite is globular here. That cannot be a martensite. But this is actually a bainite which is directly connected to the surrounding ferrite. So also here it was difficult to find the bainite. Yeah? You find the bainite only because it suddenly makes this sudden transformation of misorientations. That was the way to determine, here's a bainitic area, here's a bainitic area, here's one. The transformation is not so clear in this case. Yeah? Good. And I think, one more thing. We skip over the martensite example because I have shown that yesterday. We have all done that. This one, still not. No. This is geomaterials, which I don't want to know. No. Or not. Hey? It's not coming. So I'm in the wrong presentation. Yes. Sorry. Good. Right. I wanted to go to this one here. And that is this one here. I mentioned the presence of sigma 3 boundaries and sigma 9 boundaries. And I had already discussion with you yesterday about the CSL boundaries, and I just would like to shortly introduce this concept. The coincidence side lattice concept, which is, in principle, it's a nice geometric concept and it's simple to digest, but you will see, at least that's my opinion, in most cases it does not help very much. Yeah? But okay, it's good to know about it. So CSL stands for coincidence side lattice, and it describes a misorientation in terms of coincidences, in terms of coincident sites between misoriented lattices. What does that mean? So let me show here first a picture. Why do I write all this text? So I have here a cubic lattice, and now I'm rotating. This is the unit cell of my cubic lattice, and now I'm rotating a lattice. I take this lattice and I just rotate it by 36.87 degrees precisely. Yeah? Obviously, PowerPoint allows you to do so precise rotations. And what you see then is that actually now certain atomic sites start overlapping. Here, this one here, this one here, this one here, this one. So there's a number of sites which overlap. Exactly when you have this angular degree here, and you plot what is the lattice cell of the overlapping atoms. So the coincidence sites. And you see the coincidence site lattice is bigger than the original size, the original lattice. And actually you find it is 5 times bigger than the original one, and therefore we call this one here the volume of the CS of the coincidence site lattice divided by the volume of the base lattice is the sigma value, and this is in this case sigma 5. Yeah? So it's every 5th atom is overlapped between the two crystal structures. And of course one could say this is probably could be energetically favorable. Now, if the atoms fit, if every 5th atom fits well, this could be an energetically favorable situation. Although of course there is a sufficient amount of other atoms which do not fit, and maybe they do not fit particularly badly. No, they fit particularly badly, and maybe this increases the energy of the system again. So I'm quite skeptical whether this really means something. But who knows? At least as long as this value, sigma value, is small, there is an indication, so sigma 5 to all the way to sigma 9 or so, there could be an indication that that really has a physical meaning. But the original thing is not a physical thing, it's just geometry. So this was sigma 5, and now let me show you one beautiful picture about sigma 3. At least I think it's beautiful. So this is a sigma, it's an FCC structure looking on the 111 plane and actually plotting all the atoms on top of each other. So this is not only one layer of atoms, but it's 3 layers of atoms, one green and one yellow and one red atom. And they fit actually in this stacking order. If you look from the side on this, you see actually this stacking order, a green layer, a yellow one, a red layer, green, yellow, red. So the stacking order is ABC as we know it for FCC materials. Yeah? And if we look from top, it looks like that. And now we take this lattice and we rotate, where is it? By 60 degree, we take this, we take one lattice, we take the other one, rotate 60 degree and stick it on top again. So we do that. So, and the new lattice actually is looking like that. Again, 3 layers. I took again 3 layers. And if we now look, where do the same colors fit to each other? Yeah? Then we see of the open circles and the closed circles, then we see actually the green colors, the green atoms all fit perfectly to each other. Yeah? So there's actually, and if we plot that here, actually the new turned layer with the open circles fits in this way to the, so this is a side view again. No? And what we recognize is we did a rotation, but surprisingly this rotation leads to a mirroring. So there's a mirror plane between the upper and the lower part. We have a twin. We have created by a rotation, we have created a mirror operation, a twin. And what we find, all the green atoms coincide, and the green atoms is exactly 1/3 of the whole lattice, and that's why it is a sigma 3 boundary. Yeah? It's a 3-dimensional construction, of course, no? This sigma 3 boundary. And actually you see that here in the transition, in this cross section, exactly the green atoms fit to each other. No? They belong to both layers. So it's actually every third layer fits perfectly on each other. This is the twin. And we can now say, so this is the typical sigma 3 boundary, 60 degree 111. And if we follow a grain boundary exactly on this shared layer of atoms, then this is a perfectly coherent lattice between the top and the bottom, so we call this a coherent twin. And what is this boundary? Of course, we know it here. This is a 111 plane. So a coherent twin has not only a 111 rotation axis, which stands here, perpendicular, or stands here, but it also has a 111 boundary. And it is perfectly dense. There is actually, of course, the second layer does not fit perfectly. No? In principle, you would expect a different atom here, but the grain boundary energy of such a grain boundary, the energy of such a grain boundary is rather low. A twin is a rather dense and almost perfect structure. But the thing can change. Imagine we take the same misorientation again, the same grains here, just glued together, but I cut the grain boundary a little bit different in here. No? So I had my coherent twin here, but I have another boundary put in here. Here the atoms do not fit at all, yeah, along this boundary. They do not like each other. But this happens quite frequently. And here we have coherent, and here we have an incoherent twin, and that should be somewhere written here. Along this incoherent grain boundary, the twin behaves completely different from this coherent twin boundary. There is actually these ones here are perfect, and these ones are heavily imperfect. And you can see that nicely here in this original picture, which I showed you earlier, this one here. Up. So all these red lines are twins, and you see these twins are usually nicely straight, perfectly straight. That means they follow perfectly the 111 lines, yeah? But sometimes they start being curved here, yeah? Or here they start being curved. Or here you see it as well. It's really curved. Here is also nicely curved features. There, it cannot follow the 111 plane. No? It must be somehow an incoherent grain boundary here. So if you now would make an etching experiment or whatever kind of testing of properties, you would find, okay, the coherent twins behave very nicely, but the incoherent twins behave not nicely at all. No? We have studied a lot of solar materials, solar cell materials. The twins are no problem for the solar cell behavior at all. That's even not visible. But the incoherent twins destroy all the good properties of a solar cell. No? So that's an interesting thing that we know. Twins are an important structure, actually. No? They can be positive, they can be negative, and it depends on all 5 parameters of a grain boundary. And perhaps this one would be a good example that I sit down here again and show you this. So this allows me now, I finish my slides here again, and I make, if I find it, and if the software now is able to handle it, I will show you an example perhaps of exactly of this one here. But maybe there's a question. Yes, okay, let's do that first. Yeah.
So looking at the disorient angle in the sigma chi 60 degrees.
Yeah.
So it seems that based on the Ring-Shockley model for these dislocations, I mean for the low angle to the high angle.
Yes, right.
Boundaries,
Yes.
we put it as 15 degrees, right?
Yeah.
But now,
60 degree.
Is there any dislocation model which exists which can be able to explain this CS sigma chi?
Good question. Yeah.
There's no way
Yeah. I show you one thing. I have it all. It's incredible. No, sorry for showing off too much. Where was it? Which one was grain boundaries? This one here. Or did I close it again? I closed it again. Yes. Let's try it. This one here. No, it's not. So this must be it here. Yeah, here it is, of course. Good, yeah. So let me show this first. This is a picture of the grain boundary energy independence of misorientation. Yeah, old work from I don't know from whom it is actually. Maybe it's Gottstein and Schwindlermann, but doesn't matter. Very important data, nevertheless. And what you see here is when we are in the small angle grain boundary regime, that means here up to 15 degree, the energy constantly increases of a grain boundary. And that is simply because the dislocations get more and more. And every dislocation introduces higher energy. So, and then comes this Ricciocchi grain boundary calculation, which actually follows this line here quite precisely. And then, unfortunately, the Ricciocchi doesn't tell you anything any longer. No? And it must not tell you, because Ricciocchi is clearly only a dislocation model. No? And after that, there is no dislocation any longer. But you see, so what happens here after this, forget Ricciocchi, doesn't work. Don't make Ricciocchi calculations on a 30-degree boundary. I reject that paper, yeah? If it comes to me as a reviewer. But also if it comes to me as a doctor thesis supervisor. No, then I just kick you out of my room, of course. No, but good. More seriously again, then you see here a dip at sigma 3, which is 60 degree, 111. You see a deep dip, but this dip is not suddenly down and up, but it has again the same slope as this one here, same slope. And the reason for that is you have this perfect twin I showed you, there is no dislocation on it, and you have also no dislocation model, but the energy of the perfect twin is almost the energy of the no boundary case, yeah. But now you can actually build in dislocations into the twin. So like you do it here, you can build misfit dislocations into the twin, and then follows precisely again the Ricciocchi behavior. And it's just you're misorienting your twin more and more by building additional dislocations in. So that's actually quite simple. Yeah. So don't I have that somewhere? Because where is it? I have it somewhere, but I don't know now where. It doesn't matter. It's, for the moment, I just wanted to point out there is another. See, It becomes a little, if I describe that now in all details, then we are taking too long. There is another sigma 3 here which has not the same deep. Yeah? And that is actually the incoherent sigma 3. And why do I find it here at 120 degree? The point is actually that this is a particular sort of grain bound. This is, I think, symmetric tilt boundaries. And when you symmetric tilt boundaries, you just take the two grains, rotate them about one well-defined axis, rotate, 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 and always look what kind of grain boundary you get there. So together with the change of misorientation, you also change the plane, the grain boundary plane. And at one moment you come to a perfect twin, and another case you come to another twin misorientation, but with a different boundary. And then you are in one of these non-coherent twin boundaries, and that's the sigma 3. Why do we come to another twin? Actually, the reason is, so I said sigma 3 is one well-defined misorientation, 60 degree 111, but 60 degree 111, 60 degree around 111, is the same as 70 degree 110. And that is the same as, beat me, I don't know it, 120 degree or 86 degree around another axis. You know also the twin I can display by 576 different misorientations. Yeah? And if I constantly rotate, I come always again to a description 60 degree. I can always come back to the description 60 degree, but I can also describe it with 70 degree. And that's what they did here. They continuously rotate. They come at 60 degree, and then at, this is some other angle. This is not 70 degree, but it's some 90 degree or something. There's also certainly a sigma 3 misorientation. It's one of the list of 576 misorientation. So the sigma 3 appears several times there. No? And what else do we have here? This is still about the same axis. I think this is a calculation, this calculation probably, and this is experiment. And then this is about a different axis. Yeah, good. You have a question, yeah?
I mean, we see such results in so many papers.
Yeah.
But I really don't know how this is calculated.
How to calculate it?
Oh, this is actually not so, nowadays it's not so complicated to calculate that. At that time, when they did that, it's 60s or something like that, this was a really tough calculation. What you do nowadays is you do either ab initio or molecular dynamics. You create an atomic arrangement of this kind. So you just build up an atomic lattice in the computer, and then you calculate the energy between all the atoms, and you sum it up. Yeah, and then you change I say it's so easy, no? It's sometimes complicated to create the right structure. That's why usually molecular dynamics is the best, because in molecular dynamics, you say, okay, let me make one lattice of atoms like that, and another atom of, so one like that, and one like that. Okay, and here will be my boundary. I set that up on the computer.
In that case, maybe only for some pure metal. For example, BCC.
Yeah.
I don't know.
And now you want it for a stainless steel.
Yeah.
Then I get angry. No, but you're right. Exactly. That's the trouble. Experimentally, one. So I thought you were asking whether it can be calculated.
What is the calculation?
So the calculation, when you have a pure metal and you have a nice, I'm missing a word. I'm sorry. Interaction potential. Yeah. Then you set up a Monte Carlo. Not a Monte Carlo, a molecular dynamics simulation, and you let the atoms vibrate until some of these atoms have disappeared, and they get into a minimum, and then you get a minimum boundary structure, and this is the energy report. No? Oh, I have even a nice example on my computer, but maybe it's bringing us too far. Experimentally, you do this usually by a grain boundary grooving or by grain boundary triple junction observations. So you have you go to triple junctions, you know the misorientations, you hopefully know also what kind of planes they have, and you look what kind of angle do they form here at the triple junction. And from these angles, you can conclude on the relative energies of these grain boundaries. And if you do this for thousands of triple junctions, you can actually explore a whole set. And one group which is doing this very intensively is a group in Carnegie Mellon, Greg Rohrer. He has published a lot of papers around that, where they actually measure that. And the other thing is you can, if you have the right material, you can etch that surface. And depending on the energy of the grain boundary, the etching will go deep or less deep. So if you look on you make a cross section through here, what you see is that the material makes a grooving here. Yeah? And you measure this grooving angles, and from this grooving angle you can conclude what is the surface, what is the energy of this boundary here. Because again, you have an equilibrium between free surface and grain boundary, and this will lead to certain angular structures here. And this angulars, by measuring them, you can conclude on grain boundary energies.
This would be again possible only in some very clean microstructure like hospital.
Yes. Yeah, yeah.
Not scientific where we
Yes, and the question is whether in non-clean microstructures this has any value. That's really the question, yeah? Because often you have very strong segregation to grain boundaries. As soon as it is no longer clean, you have all kinds of effects on grain boundaries. But I have something to tell about that. But there's another question, yeah?
So are they better than the random high angle boundaries, or like in terms of energy, are they lower still?
What is lower?
Coherent sigma.
Incoherent. Some are obviously. Now, as you see, there is a little dip. This is an incoherent sigma 3 boundary. It's a little bit lower, no? And if we look into, but this one here is a calculation, and this is the experiment, yeah? And if you look here onto the sigma 3s, so this is all incoherent sigma 3s, when you have a 100 rotation, there is no dip at all. In the calculation, it seems to be a little minor, tiny little dip, but in the experiment, there is no change between a coherent boundary, between an incoherent twin boundary and a general grain boundary. And I think this is pretty true. Yeah.
And so these incoherent twins that form a part of the network, right?
What?
So like only these incoherent twin boundaries that form a part of the network, right? Random high angle network. Like if you're trying to break down a network.
Ah, you mean the grain boundary network from grain boundary engineering? Yeah, the coherent boundaries are important there, but the incoherent boundaries, so the incoherent count like boundary network breaker. So they are actually really random boundaries. Yeah, they are. You cannot take them into account as a connector between two coherent ones or so. No, they really behave different. So if you are talking about, for example, progress of corrosion or something like that, it will corrode at these incoherent sigma 3s. Yeah, or maybe you want to break that network of twins. Then the incoherent ones are good, yeah. But why would you like to do that? Usually you want to have a network of twins and not break that network. Yeah, the incoherent ones don't help you in this regard. Okay? Yeah? Yes, right.
I need to understand the concept that while there is like a spread in the tip,
Why is there?
spread, there is a spread in the tip. During the tipping,
Yeah, you mean this one, yeah? Yeah. This is actually, so it's like this one here. There is the, you can have a set of dislocations turning it away from the twin boundary to a larger misorientation, or turning it to closer, to smaller misorientations. Yeah, so going towards 65, from 60 to 56, or going from 60 to 64. And in both cases, it's the same amount of dislocations necessary, and that's why this valley here is actually symmetric. Yeah, so that's the reason why you have this opening here. And then there is this Brandon criterion. You may be aware of that, no? Which just says if you are so and so far away from a particular grain boundary, then it still counts as a grain boundary. No? And that depends on which kind of coherency you have. And it comes actually from this So Brandon considered the amount of dislocations you need in order to deviate from a certain CSL grain boundary. That's where the Brandon criterion comes from. No? I will not explain for the others the Brandon criterion. This is expert talk now. No, but maybe everyone knows here. No? Yes. Let me show you this one example, if I find it. Because this is so great, yeah. I'm so excited about myself. No, sorry. We make a break very soon. You may be not so excited about me because I'm talking too much. Where is it? Which one is it? Silicon superlayer. I should have this austenite texture. Where is it? No. No. I have steel and silicon, super recording, alpha gamma. I don't find it in the moment. I have recrystallization. It sounds like the first one. Texture test. So, okay. When did I start? At 2 o'clock, no? And now we have 1.5 hours talking. So maybe we'll make a break right now. I look for this example, and we work with some examples further after the break for maximum one more hour. Yeah? How much do we take usually? 20 minutes or something like that? So 10 to 4 or something like that, or so shortly to 4, or maybe at around 4 o'clock we start again. Yeah? Good. All right? Good.